Hi, it's time for another math easy solution. Today we're going to discuss further into differential equations and now look at example 3 of the predator-prey systems video series that I've been going over. And before I get to it, like always, you can download these exact notes in the link in the video description below. Also, subscribe via my email newsletter at mes.fm/subscribe and donate at mes.fm/donate if you like my videos. Anyways, so let's moving on to this example. It states each of the system of differential equations below, it's these ones right here, A and B, there's two sets of differential equations, both of them representing one model, and is a model for two species that either compete for the same resources or cooperate for mutual benefit. An example of mutual benefit is flowering plants and insect pollinators, for example, or for instance, where basically the more flowers that there are, then there's more insects can increase in their population size, and then when there's more insects, and then they can pollinate more flowers, etc. So they're both mutually benefiting. And this is a bit different from my earlier videos on predator-prey, where the predator eats the prey and the prey has its own food supply. So these are slightly different models for these two species types. So, and in this example, we're asked to decide whether each system describes competition or cooperation and explain why it is a reasonable model. And then a hint that my calculus book gave was ask yourself what effect an increase in one species has on the growth rate of the other one. Yes, so we have part A. This is one model right here. We have dx over dt equals to 0.12x minus 0.0006x squared plus 0.00001xy, and then where the growth rate of the y population, dy over dt equals 0.08x plus 0.00004xy, and we'll go over part B afterwards. So we have to find out if it's a competition or a cooperation type model. Yes, so now let's look at part A, and then first of all let's look at the first differential equation in part A, which is the dx over dt. So I'll just put an arrow there. So what we have is dx over dt, and what I'm going to do here is factor out this 0.12x, because there's an x and there's an x squared there, just to show that this is in fact the first term is a logistic equation. So if we factor out the 0.12x, then what we have is a 1 minus, and this is 3 zeros and a 6. So we have 1, 2, 3, 6, and then there's an x because it was x squared we factored out. And when we factor out, we have to divide by 0.12. So if you expand this out, 0.12x just becomes the same equation as above. And then what we have now is a plus, and then there's 4 zeros, 1 xy. So plus, okay, so plus 4 zeros, 3, 1 xy. Yeah, so now what we get is, well, if we just divide this out, this number right there, just remove the decimal places and make it a number at the bottom, just to show that it's a logistic equation. So if we divide this out, 0.112, and this is how many? This is 4 decimal places, so we go 1, 2, 3, 4. So if we multiply this out by 4, so 10,000 like that, and 10,000 at the bottom, just to get rid of this decimal place on the top. What we get is now this equals to 6 over, and then this goes 1, 2, and then 1, 2. So we'll have 2 zeros elsewhere. So we have over here, like that, 1200. And now if we divide this out, this 6 goes into a 12 2 times. This just becomes, well, 2. This is 1. So we get 200. This is 1 over 200. So what this means is we can rewrite this as dx over dt, write this d meter, equals to 0.112x, and then 1 minus, and then we have an x over 200, and then plus 0.00001xy. And again, this is exactly the logistic model. And you can see my earlier videos on that. So this is a logistic model. The first term is that. Yeah, so what we have here now is basically, well, the growth rate of x consists of a logistic model term, that's this one here, and an xy term right here is 0.0001xy. And then where this one represents the encounters with y. So the only place where y occurs in this growth rate of x is over on here. So basically, when there's increase of y, this is what the term that is affects the growth rate. In other words, it represents the encounters with y of the x population. So the logistic model term represents the growth of x independently from y and up to a carrying capacity of 200. So if we ignore the y here, so if y is 0, what we'll end up getting is just this logistic model where the growth rate of x increases up to the carrying capacity of 200. So that's when we look at the term independently from y. And since xy term is added to the logistic term, this means that as x and or y increase, the overall growth rate of x also increases. And that's because here, this model just goes up to 200 independently of y, but then as you can see here, as you increase y as well as increase x, they're both increasing this term. So this is a positive right here. So then when you increase x and y, this also increases. So this increases. So, and we'll get to what this means later. So this is probably a cooperation model, which in fact it is. So let's just look at the second differential equation. So the second one up here is dy over dt equals 0.08x and then 0.00004xy. So dy over dt equals to 0.08x plus 0.00004xy. Yeah, now in this one right here, notice that every term is positive. So since every term is positive, the growth rate of y increases whenever x and or y increase right here. So when this increases, when x or xy increases, then dy over dt increases. So basically, both of these models, or this population of x and y, are dependent on each other in a cooperation model. So thus the system of differential equations describing a cooperation model, because as either of the populations increases, the growth rates for both increase, which is, yeah, so that's pretty much the cooperation model. So now let's look at part B. So the part B, the model is dx over dt equals 0.15x minus 0.0002x squared minus 0.0006xy, and then the dy over dt, the growth rate of the y population, is 0.2y minus 0.00008y squared minus 0.0002xy. So again, let's start with the first term. So the first term was, again, just to recap here, so 0.15, and then there's 3 zeros, 2, 3 zeros, and 6. So we have a dx over dt equals to 0.15x minus 3 zeros, and I think it was a 2. Yeah, 2x squared, and then minus 3 zeros and a 6. 1, 2, 3, 6x, y. And just to double check, so we have 3 zeros and a 2, and then 3 zeros and a 6. Okay. And again, the same thing I'm going to do is factor out the 0.15x to show you it is a it's the same thing as before, where you had a logistic model, but yeah, so we have 2x like that divided by 0.15, and then minus 0.0006xy. So again, this is a logistic model. Just divide this out, just for completeness sake, to see how it looks like. It's 0.0002 divided by 0.15. Multiplied by the number of decimal places here, 1, 2, 3, 4, so 10,000 again, 4 zeros. This equals 2, so this goes over 2 over, and then we have 1, 5, 1, 2, and then 1, 2, some more, so 0, 0, 1500, and then this goes into 1, this is, well, 7.5 times 100, we get 7500, or I mean just 750, so 750 like that, 7.5 times it by 100, 750. So we have this equaling 2 dx over dt equals 2.15x, and then 1 minus x over 750, like that, and then this minus is 0.0006xy. y. So again, we have a logistic model term, but now we have a negative right here, meaning that the growth rate of x decreases when you increase y. When you increase the y, it actually decreases, as well as increasing x, because that indirectly increases y as well. Yeah, so we've written it down here. So similarly to part A, the logistic term shows that in the absence of y, that x increases to a carrying capacity, this time of 750. And since we are subtracting the xy term right here, this indicates that the growth rate of x decreases as the number of encounters of x and y increases. And again, that always represents the encounters because there's a y term there. So this decreases. So we have a decrease when this term increases. And then now let's look at the second term of it. And as you can see, this might be indicating that they're competing for resources, because when there's increase encounters, decreased growth rate, etc. So this behavior is the exact same for the second differential equation as well. Let's see what that was. These are just some long equations, hard to memorize. So the same thing, but now I'm going to factor out the 0.2 out, and there's a 4 zeros now, 8, and then 3 zeros, 2, and they're both negative. So what we have is a dy over dt equals 2, and this was just factored out, so 0.2y, then we have a 1 minus, there was 4 zeros, and then 8, and then there's a y, it was y squared earlier, so then we take out a y, and then this becomes, over here, 0.2, and then minus, and then this is 3 zeros and a 2xy. And just to double check, let's go up here. So we have 4 zeros and an 8, there's 0.2, and then there's 3 zeros and a 2, and they're all negative, etc. And xy, like that. So let's just divide these out, just do some, again, division here. So 0.00, there's 4 zeros, there's 5 decimal places, and then this, move it over 5 times, so 1, 2, 3, 4, 5. Same thing as writing it now by 100,000. Just to get rid of the decimal place, this equals 8 over, then we have 1, and then we have followed by 4 zeros. And then there's going to be 2, 1, 2, 3, 4, and then this one we can just divide this out by 2, that's 4, this is 1, so we have 4 over 4 over 1,000, oh, 10,000. And again, it's the same thing as having 2,500. So this is, we could cancel this out. 1 and 1 goes into 125 times. Yeah, and then add the 2 zeros, so we have this 2500. So in this case, the carrying capacity, again, it's the same thing. We have a logistic model term. We have a carrying capacity of 2,500. So what we have now, put this arrow like that, dy over dt is equal to 0.2y, 1 minus y over 2500, then minus 0.0002xy, like that. And now if we notice here, this term and this term are pretty much identical in the form, just different values. So they're the exact same type. So the growth rate of y grows independently of x until a carrying capacity of 2,500. So if there's no x right here, if that's a 0, then this just grows until carrying capacity 2,500, just because it's a logistic model. But as the number of encounters of an x and y increase, represented by the xy term, then the growth rate decreases. So basically, if you increase this term, this decreases, like that. In exactly the same form here. So increase, decrease. So thus, this system of differential equations is describing a competition model in which both populations are competing for the same resource. So when you have increase of one population, it's eating up more of the same resource that the other one needs, hence decreasing the other's population. And then it works both ways, vice versa. Increase of x, decrease in y, increase of y, decrease in x. So that's a competition model, and this above one is a cooperation model, and that's pretty. That's pretty much represented mainly by this plus term. So this one's positive there. Yeah, so whenever you have a plus when there's an xy term, that means that this term is benefiting from the other one, and then in this case, both of them have it for the first part, A. So they both have positive, they're both increasing whenever there's an increase of the other population, but on this side you have a decreasing whenever here. And I just wanted to go into more detail, show it's a logistic model, etc. Anyways, that's all for today. Hopefully you all learned, and like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.